Hello, everyone. My name is Martin, and I work at Sintef, which is an independent research organization based here in Norway. I'm a part of Team Axiom 1, that also consists of Geir Hasle and Magnus Stålhane. On behalf of the team, I'm going to present the method we have used in the Dymax VRP challenge. And the method is called hybrid genetic search with ruin and recreate. So in order to explain the solver we have used, we first have to cover some background information. The solver is combining two of the best methods currently in the literature. The first one is the hybrid genetic search by Vidal, more specifically the recent version that is specialized for the capacitated weak routing problem. The second method is called slack induction by string removals, or scissors for short, and it was proposed by Christians and van den Berge. Given the time limitation of the presentation, I'm not going to describe these methods in detail, but I will attempt to give a quick introduction. For further details, I definitely recommend reading the original papers. So, starting with the HGS, it is a population-based genetic algorithm. However, in contrast to a standard genetic algorithm, it does not perform random mutations. Instead, it improves or educates the offspring solutions by doing local search. The local search consists of 10 different neighborhood types, including several versions of relocation, swap, and to-opt. Additionally, it has advanced mechanisms for maintaining and controlling the diversity of the population. Scissor, on the other hand, is a neighborhood-centered method which performs a large neighborhood search that is defined by a set of ruin and recreate operators. The idea behind the method is to induce both spatial and capacity slack into the solution. And this is achieved by removing or ruining a set of customers or strings of customers that are adjacent across multiple routes. The ruin and recreate process is, and whether to accept the recreated solution, is controlled by a simulated annealing meta-heuristic, where the probability of accepting a worsening solution decreases exponentially over time. With the methods introduced, I also want to quickly mention the trade-off or balance between exploration and exploitation that occurs when you're designing a heuristic method for CVRP or any other difficult optimization problem. Let's imagine if the search space or the search space of possible solutions is very large and you have limited time to solve the problem. You might want to focus more on exploitation so that you find an acceptable solution at all within the time you have. But on the other side, insufficient exploration might get you stuck in a local optimum that might be far away from the global optimum. So I'll keep coming back to this balance throughout the presentation, so please keep it in mind. Okay, so with the background in place, I'm going to present to you two of the research questions we had and that we wanted to answer. The first one is it possible to gain performance by adding ruin and recreate as a component in the education phase of the hybrid genetic search? Hopefully, ruin and recreate can find good solutions that the local search could not find, but it might not be worth the extra time it requires as it will result in each iteration of the genetic cycle becoming slower. So then it's back to the balance. If you spend more time improving a single solution, you're more focused on exploit compared to giving the genetic algorithm more iterations to evolve the population. And the second question was, what is the effect of devoting computational efforts to the creation of an elite solution in the initial population of HGS? Remember that HGS is evolving a population of solutions. What if we instead spend some time trying to quickly find a single good solution? This is done in an intensified search we have called elite education. And the hope is that it will speed up the convergence and hopefully improve the primal integral. So yeah, to answer the research questions, we implemented the hybrid genetic search with Ruin and Recreate, and we performed a series of experiments with it. As I said, the method is an extended version of the HDS. If we take a look at the figure, we have illustrated the method with 7 components that form the genetic cycle. The first step in the genetic cycle is to select parent solutions, which can then be recombined into an offspring solution in the second component. Because the recombination is performed on a giant TOR representation, the TOR must be split into roots, and that responsibility lies in the third component. The offspring solution is then improved with a local search and further improved by the Ruin and Recreate search in component 5. The last 2 steps consist of evaluating the solution's fitness relative to the population, and then determining whether it's going to survive as a part of the population into the next iteration. So if we remove the 5th component with Ruin and Recreate, the method is the same as the original HDS. And as we'll see later, the elite education relies on the same components as regular education, but it spends significantly more time in the 5th component with Ruin and Recreate. So to summarize the method, the only addition to the HDS is the 5th component with Ruin and Recreate search, and it is used in 2 different ways, during regular education and during elite education. So if we then continue to the first experiment, that is the RNR search in the regular education. So to first explain the RNR search, it is controlled by 2 parameters. The first one is denoted gamma, and it is multiplied with the instance size to determine the number of iterations or moves with Ruin and Recreate to attempt. The second parameter is T0. That is the starting temperature of the simulated annealing that is controlling the RNR search. So if you look at the figures on the right, we are presenting some parameter combinations of gamma and T0 that we tested on a subset of the X instances. And from the figures, we see that from the top figures, you see that starting temperature of 1 and 10, that is relatively low. Then we see that adding Ruin and Recreate improves the performance compared to the original HDS. Note that the original HDS is the same as setting gamma to 0. But on the other hand, if the starting temperature is higher, meaning that the probability of accepting worsening moves are higher, the method performs worse. If we continue to the elite education, we have the same parameters as before, but now the values are different. Remember that we want to spend much longer time in the elite education compared to the regular education. Therefore, the parameters are denoted with a superscript E. If you then again take a look at the figures are similar as before, where each subfigure is a different value for the starting temperature, and each line in the figure is a different value for the gamma. Then I would like to focus on the bottom left figure, where the starting temperature is 50. Then we see it as we increase gamma E, we spend more and more time on a single solution before the genetic algorithm kicks in. And if you take a look at the red line, or the line with circles, that's like the baseline, because we previously chosen gamma E or gamma to be 1 in the regular education. So in that case, we have no education at all. And what is interesting is that if you look at the subfigure in the bottom left, all of the ones with elite education end up below the one without. And you also see that some of them, especially the blue line and the green line, lies below all the time. If we continue, yeah, so in the end, we also did a full benchmark test where we compared the HGS RR against the original HGS and also the sister heuristic on the X instances. So we have chosen to use 2 different configurations of the method where they have different values of the gamma E, and that's because the previous experiments show that a higher value of gamma E is beneficial for the best final gap compared to achieving the best primal integral. So if you take a look at the table, HGS RR1, which have a gamma E of 10,000, that's the method that achieved the best primal integral. And that you can see is the blue line in the figure. While on the other hand, HGS RR2, which has a much higher value of gamma E of 100,000, that means we spent much more time on a single solution before we started the genetic algorithm. But that means that the genetic algorithm starts from a better solution. And in the end, it received a better final gap to the best known solutions, but the primal integral wasn't as good. So since the Dymax challenge evaluates the primal integral, we have used the parameter configuration of HGS R1 in the competition. Yeah, just to summarize, I want to go back to the research questions. So the first one, is it possible to gain performance by adding RNR rate rate? Yes, at least according to the experiments we did. It seems like RNR rate rate improves the performance as long as the starting temperature or the probability of accepting worsening moves is relatively low. And the second question was, how is the, or what is the effect of devoting effort towards elite education before you start the HGS? And from the second experiment, we saw that depending on the parameter configuration, the elite education may improve both the primal integral and the final gap. So, yeah, I think that's what we had. Yeah, there's a few references. Then I just want to finish off with saying thank you for listening.